This is part 2 of mechanical vibrations. So as you may remember, this is the equation of motion derived from Newton's second law. And now we proceed to consider a particular case. So we're going to make an assumption here. We're going to assume that this term here is a constant function equal to 0, and that would mean that we're considering what is called free motion. And also we're going to consider that this parameter, this constant for damping, is equal to 0 as well. And in such case, we would have a system that has no damping, is undamped, and is also considered free, or it's not subject to an external force, or is unforced. This reduces the equation to m times x double prime plus k times x equals 0. This is a homogeneous problem. The coefficients are constant, and so we could proceed as as we know, like we can assume the solution. Well, but part of what we're assuming here is that x, which is called the state variable, displacement as function of time, we can assume that solution has form e to the rt, right? And then we can continue on computing characteristic polynomial, the equation, and so on, right? But before we do that, let's manipulate the constants, these constant coefficients in a certain way. For example, let's divide every term here by the non-zero constant m. Okay, we divide by m in every term of this equation, and this would imply that we have the leading highest order derivative here with coefficient 1, and we still have a constant coefficient multiplying the variable x, the state variable x, and this is equal to 0. So let's suppose that this coefficient k over m is renamed as another parameter, and conveniently we're going to assume that that parameter is called omega 0. It looks like a w, but it's omega 0, and we're going to assume that's actually omega 0 squared. That is the same as assuming that the square root of k over m is equal to omega 0. So if we make that assumption, then we can rewrite this equation as x double prime plus constant omega 0 squared times x equal to 0. Okay, so now we can derive the characteristic polynomial, characteristic equation for this. So we can compute the first and second derivative of y, of x. In this case, we're going to state variable x, and this would be what we call the characteristic equation, characteristic polynomial. We're looking for the roots of this characteristic polynomial, and so solving for r in that equation, we find r1 bar and r2 bar. They are complex conjugates of each other, and they are of the form basically it's plus minus I omega 0, right? So this means that the real part of both of these roots is 0. These are purely imaginary numbers that lie on the imaginary axis of the complex plane, and here the imaginary part is given by this term here. The imaginary part is given by omega. So in fact, the imaginary part is minus omega, positive omega, depending on which complex conjugate we are considering. But what we know is that based on the real parts and the imaginary parts of these complex roots, then the solution of this second order linear differential equation with constant coefficients, that solution in this case is the result we know is x of t. Is going to be a linear combination involving sines and cosines. So that solution would have cosine, sine, and it really would involve e to the 0 times t. The real part of these complex conjugate numbers are, the real part is equal to 0, so e to the 0 is 1, and the argument of the sine cosine function in this case would be omega 0 times t, and then we have the constants, which in this case we could call them c1 or c2, right? So we could write something like c1, c2, and this would be the general solution of that second order linear differential equation with constant coefficients. So let's remember one of those formulas from one of those trigonometric identities. This is one that has to do with the argument of the cosine function. You could think of this as being an addition with a second thing that's being added here as negative beta, but it's a subtraction. So this formula for the difference of angles becomes a sum of two things, and so we have here cosine of alpha, cosine of beta, and here we would have sine of alpha, sine of beta. Okay, so what we want to do is to use this formula. Okay, so in view of that identity, so let's now consider cosine. We're going to consider the cosine of omega t minus gamma, where gamma is a constant. So this becomes cosine of omega t multiplied by cosine of gamma and sine of omega t multiplied by sine of gamma. So because of this, we're going to rewrite the solution of that differential equation. We should consider multiplying by a constant. So let's suppose we multiply by a constant here called c in both sides of this identity. And now we're going to collect maybe the terms here on the right hand side. We're going to collect c, let's say that c and cosine gamma, and here we have c multiplying sine gamma. Gamma is a constant, and therefore cosine and sine evaluated at this constant is also another constant value. So we can rewrite the terms in this way, and in fact we can think of this a constant times another constant. We're going to call this constant name a, and we're going to think of this product of two constants as, we're going to rename that as a new constant b. So this now is looking like a cosine omega t plus b sine omega t, right? And so this is exactly the form that we had derived, right? So here's the solution to the second order linear ODE with constant coefficients. Here the constant is omega, basically. That solution is expressed as a linear combination of cosine and sine, and we have those constants in front of it. But basically, because of the derivation we just worked out, we can rewrite the solution. We can rewrite this. Basically, this is equal to c times cosine of omega t minus gamma, where c is a constant different from c1 and c2, right? Because that linear combination of cosine and sine now depends on these constants. I'm calling a and b. They're going to have to do something. They're going to be related to the c1 and c2 that we had there, right? So yeah, so let's just think of here, let's think of c1 as being a, and let's think of c2 as being b. And then the question is, well, if we express this now, the solution as x of t as a constancy of cosine, the only thing that's changing here with t is this product, omega 0 times t. And well, you may wonder, but how do we compute this new constant c, assuming that we know constants a and b, or c1 and c2? That's not a problem. Okay, so how to compute c? Well, let's remember that we have a equals c cosine of gamma, and we have b equals c sine of gamma. Then let's consider the square of each of these terms, and let's add up the squares, right? And so this would give us c squared. We could factor c squared, cosine, the square of cosine plus the square of sine of gamma. And this means that this becomes c squared. So it's not difficult to see that the square root, okay, that c can be obtained from the square root of the sum of squares, a squared plus b squared. This should be very familiar because it's directly related to basic trigonometry, right? So this is how we compute c. But what about gamma? So gamma is a constant, okay? Gamma is a constant that appears in this new formulation. And you may wonder, well, so, you know, what do we do about gamma? Well, no problem. Let's address what about gamma. We can compute gamma, also based on basic trigonometry, because let's divide b over a. Okay, if we divide, here's the definition of b, c times sine of gamma. There is the definition of a. We divide b over a, the c's are going to cancel, and we will obtain that this is equal to tangent of gamma. From where we can solve for gamma by taking the inverse tangent of the ratio b over a, or this is also what is commonly referred as the arctangent, right? The arctangent of this quantity. We take the arctangent or tangent inverse of the ratio b over a, that will give us gamma. So there's a way of computing gamma, there is a way of computing c, right? And remember, b and a, or a and b, are the constants. Assuming we know these constants a and b, then we can compute this new constant c, and we can compute this new constant gamma. Gamma is a constant that is formally called the phase shift, and this is a parameter, a constant, that takes care of shifting the graph of the cosine function, from the left to the right, or from the right to the left, when we're considering now the solution of that equation as basically a cosine function, this cosine function, right? And by having that constant there, this is a function of t, right? The independent variable here is the variable t. So if you're thinking of the cosine function versus t, then this effect of this constant will be shifting that cosine function from right to left, or left to right. The parameter c, which is the constant that appears in front of the solution, this parameter c is going to be considered, formally called, the amplitude, right? And so the amplitude has to do with basically this dimension, or this length. And the constant omega sub 0, remember, is defined as square root of k over m, is dubbed the natural frequency. So with this setup, expressing the solution of this second order equation, in this way, which is taking into account the amplitude, phase shift, and that frequency, angular frequency, then we are addressing something that's usually called simple harmonic motion. So this being the solution of this second order equation, either of them will be called simple harmonic motion.